Hi all, welcome to Theoretically Podcasting. I have the great pleasure of welcoming Professor Gabriele Carcassi to my podcast today. Welcome, Gabriele.
I'm not a professor, though.
Okay. Apologies.
It's okay.
So then please tell us what you are and what you do at the University of Michigan.
I'm a researcher at the University of Michigan, and I have this research project on fundamental foundations of physics called Assumptions of Physics, which aims to find a minimal set of physical assumptions where we can rederive the theories. And so the idea is to understand what is the realm of applicability, say, of classical mechanics, quantum mechanics, thermodynamics in a precise way, such that we can then reconstruct it from scratch, from just laying out mathematically the axioms and the definitions, or always having a tight justification of why we're taking those axioms, why we're taking those definitions.
Wonderful. So you briefly mentioned to me prior to our recording your very interesting path towards physics, which I think my listeners would be very appreciative of. So could you briefly walk us through what led you to this ambitious project?
So I originally, my degree is actually in engineering, in informatics engineering. This is the type of degree that really software. It's more than software, but it's not electrical engineering. It's somewhere in between. And I basically kept a side curiosity for physics. One of the reasons I went to engineering is because I thought I would get more breadth in terms of things, which was true. I mean, all the things that I learned about control theory or system theory or chaos theory, all these other things that I had to learn, or signal processing, all these other things that I had to learn as part of engineering actually then helped me quite a lot in the foundational process, because it gives you multiple ways of attack the same problem. But anyway, so I did engineering, and I basically did software in essentially high energy physics. I worked on various experiments at CERN, at Brookhaven National Lab. I worked from control system to databases to essentially things that need to be done. But as a side, I always had these physics questions, and I kept sort of learning more and more, just because I'm in the environment. I had access to free auditing at the university and so on. And so I built I built a background, and then after some time, sort of my focus shifted from the sort of the software engineering side of things to actually more fundamental research. And really the thing that interests me more is the connection between foundation of mathematics, foundations of physics, and the philosophy that you need to bridge all these things.
Oh, that is a very fascinating path. I mean, it's one of those old adages that people almost take for granted, that the engineers are the ones that are most agnostic towards whatever the foundations we think are. They really just want to make whatever it is work. And, we're very grateful for them for that. And, there's this sense that we ought not to bother them with all of these things. So that I came across your work in preparation for the previous episode on this podcast, which was interview of Julian Barber, our mutual acquaintance. And in particular, it was a paper you'd written with him, Professor Aidala, about variability as I don't exactly remember the title. Of course, we'll share it, but basically identifying Shannon entropy as a measure of variability,
Right.
and that this is sort of the right way to think about it. And you convinced at least me that it certainly is. And I really felt like it would be great to discuss this on this podcast. Even though I should mention, and I will put this in the description, that you have a very nice series of videos where you do explain exactly all the ideas that go into that paper with very nice illustrations and so forth. But so at risk of being redundant with that, I thought that I'd persist and ask you about this paper, because it is a concept that is ubiquitous, as you mentioned, And we have quite a lot of, well, even my colleagues here at the SITP put quite a lot of effort into computing quantities they call entropies in all sorts of ways. Nevertheless, I find that the basic discussion of what exactly it is gets a little bit buried. So in some sense, we ourselves sometimes act as this sort of the straw man engineers that I described it at the outset, and it was really sort of refreshing to see that needn't be so. So without further ado, I'll just begin by sharing the paper. So this is the one. So could you briefly tell us how this paper came to be?
Yes, so the paper came to be because, again, as part of our project, I think in 2018, 2019, we started to look at the foundations of thermodynamics. We basically had concluded what we wanted to do on the foundation of classical mechanics and quantum mechanics on identifying what are the sort of assumptions that we need for getting those theory going. And so we basically said, okay, let's start looking at thermodynamics. And in our naivety, we thought that since thermodynamics exists for a lot longer than some of the theory, that it would be super easy. You just go and read the papers, and instead, when we had different students report on what they were reading, the thing was so confusing that when the students was presenting, both me and Professor Vidal, we were confused. I said, okay, the students hasn't done properly the work to understand. And then he basically just gave us the quotes and said, okay, it's completely unintelligible. And it was interesting because there are all these people in the literature that sort of argue for their own true way of understanding entropy. And then you go and try to look at and try to make sense of it, and sometimes you don't understand, or you understand that one person is actually talking about a different thing that the other person is doing, so they're just talking past each other, and so it was complete confusion. And to try to understand a little bit better, what I did, I joined a summer workshop, summer class on summer school. There you go, a philosophy summer school of entropy in the woods of south of Germany, and there was a presentation from a philosopher that it was probably the worst presentation, quite frankly, that I've ever seen. It's like he had to talk about Shannon entropy, and again, since I have my background in engineering and in software engineering, and information theory is something that I learned and it's dear to me, and he completely butchered it. I mean, he started essentially ranting on how bad this thing was, and how sort of it came out of nowhere. And I had to raise my hand. It's like, it doesn't come from nowhere. If you look at the original paper from Shannon, he lays 3 specific conditions that that thing has to satisfy, and he derives it. He wasn't aware of that. And then he kept making confusion between coding and compression, right? As if they were the same thing. He was heckling the students that they were making. It was like a surreal experience to me, I have to say. And I was a little bit disheartened, and I didn't know Julian at the time, so we started discussing, and as I was saying, there is a way to understand these things a lot better. Like it's not, it doesn't come out of nowhere. Nothing comes out of, like, if you don't understand where it's come from, most likely you are not understanding where it's coming from. And so we started discussing, and then he liked this idea of variability, and then he actually graciously hosted me at his place, and I spent 1 week there so that we would write the paper together. So this is the story, and the whole thing. But yeah, there is, as you said, there is a lot of confusion, and part of the confusion is also that what I feel that these concepts are applied not uniformly in different fields, and fields have developed their own way of thinking that sort of works for their own specific things, and then of course they don't care about anything else. And so, for example, people who do Bayesian statistics that have a Bayesian view of this as agent information. That, of course, is not going to work if you're trying to do thermodynamics, where things have to be more objectives because they have to come from physical processes. And then you have people that sort of fight against each other because, I know it can't be this, it can't be that. And so basically then we said, okay, let's try to get some order here, and let's try to identify again, like in the spirit of my project, a minimal set of requirements that tells me exactly what this thing is, but not in a vague way. I can sort of understand it as I don't know, what are the things that typically people say, that uncertainty or disorder. No, something has to
information.
Right, so that you can write down, you can encode your ideas in mathematical form, and then you put the mathematical form, and then you show that you actually derived that expression. Otherwise, you don't know what you're talking about, essentially.
Indeed. Well, I mean, I have to say that I've always found it difficult to sort of swallow the whole, well, it's the disorder, it's the lack of information, it is somehow also the information. Well, simultaneously. And so it usually, so I mean, I have to say that where I felt an analogous level of clarity was reading when I read back when I was still studying the volume 4 of Landau and Lifshitz, which was the first statistical physics volume. And there, at least for the microcanonical ensemble, there's a sort of at least a self-consistent definition of what the entropy ought to mean. And a little bit of a nod towards some of the other intuitions later when the other ensembles are introduced. But it's actually interesting now to think back at which version, as we'll go through. So basically, you very nicely lay out the sort of different notions of distributions you have, and the different roles that the entropy plays in each of those kinds of distributions, of either credence, this is the sort of a population statistics or sort of probability distribution, and how in each of these cases you have to have a different, I mean, the entropy means something different, or combinatorics. And actually this combinatorial one is the one that they actually use in effect. And you know, it's like, it's also historically the kind of thing that Shannon was kind of making sense of in his in his information theory sort of work. But you sort of do delineate the differences between these, and it is curious that we do have a setting where there's the combinatorial one, and then, you know, when we start to think in terms of the canonical ensemble, we rather want another kind, which I mean, of course, it's consistent. It's just important to sort of like remember what the various definitions we usually go with are. So I suppose we should begin with your well, I mean, as you do with the basic premise that, well, the answer rather, to sort of set aside all the confusion, sort of have the answer, and then we'll sort of work backwards from there. So as the title suggests, you discuss how the right way to think about Shannon entropy is about variability within a distribution. So how did all of this sort of converge towards this idea about variability, like all of your thinking?
Oh, I can't tell you how I get there. I like the way that I work is that whenever there is something confusing, I go and look as much as possible as different things, given even more confused. And then at some point, my brain sorts out, actually, that part is kind of similar to that part. And that part, no, that part is just a mistake. And then it sorts it out. And this is the answer that I got, but I can't.
Okay, I see. So perhaps it was.
I don't know how my brain works. So basically, you know, I must have tried different solutions, and this was the one that. I mean, I was aware of the use of entropy in ecology, for example, where and this is a whole set of other interesting stories. Because there was a workshop here, I don't even remember, in 2016 maybe, about essentially the use of entropy maximization in all sorts of different things. And it was parts in economics, parts in ecology. So that's where I was more exposed to the use of thermodynamics idea outside of physics. And it's absolutely, and again, I can't. If I go in detail, all the stories we're never going to go anywhere. So. But so I was aware of that. I was aware of the Shannon definition in his original paper, how he derives it, and that was particularly disappointing to me because even when I studied these topics at university, the entropy function was essentially set there without justification, and
Right.
it's particularly sad to me to see that the guy who like invented this tool actually had not just a strong justification, had a derivation for it. And this somehow is not reported in most of the textbooks. Most of the textbooks just said it. So anyway, I was
Indeed.
aware of the paper, so I was aware what it sort of needed to justify at that level. And then I sort of put it all together, and I think that the derivation that we came up with is slightly cleaner than what Shannon did, but it's basically equivalent. And so the main thing that I needed to do is that the way that what was Shannon characterizing was basically the information. Again, information is a bad term. Is the data that is actually transferred on a channel, right? So he was imagining there is a source, there is a destination, I have to transfer data from one to the other. How can I numerically characterize that? Because his main problem was to define what is the best capacity for a channel. That was a very practical engineering problem. How much data can I go through that? And he sort of single-mindedly created all this theory that created an upper bound, like the maximum amount of information. And only I think in the late 90s, an algorithm was actually found that saturated the bound so that now all our like a GSM and so on, I use those encodings so that we actually saturate the bounds. And so the idea was essentially, since probably I had this idea in my head, the idea is to understand that the information that we are transferring, what we're really trying to find is the variability of the source. And if you have a source that, it's the typical example, if you have it is temperature is above 20 degrees or below 20 degrees. If you are in a desert, you are mostly gonna get above 20 degrees. Then sometimes goes down. So once it gets down, it's more information. And if you have something that instead of a spread 50-50 that it's going up and down, you get equal amount of information for both answers, but you also have more data to transfer, and that's basically the idea. You have increased the variability of the source, and the more the variability increases, the more you have transfer information. So that's the idea. And so going back, you basically say, okay, suppose I just have a set of things, right? And it could be a finite set or an infinite set. But the important thing is that you can create a statistics, right? You can say, okay, this text, this set is made of shapes. So there are stars and circles and the squares, and then you count how many there are, and you can say, okay, 50% are this, 30% of this, and so on. And so the idea we want to have as a sense is that if you can imagine that if there is a set that is 99% stars and 1% circles, it has, all the elements are kind of the same, where if something where it's 50% stars and 50% circle is more varied. And so the idea is to make that more precise. And then that same intuition can be transferred to, as I said, information. You have a source is emitting symbols, and you're asking, well, how much is the variability of those symbols? Or you have, in ecology, you have different types of species and so on. And so you ask, how, like, not just how many species you have, because how many elements of each species that you have is also important, and so you want to have a measure of variability for that as well. In economics, it's going to be the same things, and in statistical mechanics is the same thing. If you imagine that you have your microstate that is jiggling around because of your external interaction, because there is temperature and it's outside, there is this exchange of energy, well, that is introducing variability in the system, and so you want to say, okay, how much variability there is.
Right.
And the thing is that once you have these 3 vanilla conditions that you would like to have, you get the Shannon entropy without any other consideration.
Great. So basically, just to summarize, you have a set of elements, and basically that means you have some criterion by which to distinguish them. So you have like
Yes.
n classes of a thing. You just start by figuring out what the counts are, and then you sort of just divide by the total number. So then you have basically the relative occurrences of each of these, and the entropy is basically going to tell us how, take this, put it through a formula, and give us a number that says how varied is this distribution of elements, right? So that's the sort of overarching picture that unifies maybe all of these different uses of the idea. And that was very clarifying indeed to notice. And yeah, a few other things that you do mention in your videos, which I think are worth going over, is that what matters is, of course, these relative frequencies themselves, as opposed to the actual value of whatever this E alpha is. That's almost irrelevant to the question of being able to characterize the variability. And hence the concept is applicable in so many different domains, because it doesn't actually need that you're talking about like velocities of particles or some very, very narrow niche. So let's try and get to those criteria that you mentioned that basically Shannon had identified as what this quantity ought to satisfy. So to convince everyone that the formula doesn't come out of nowhere.
Right.
So these are the requirements.
Yeah, so as you said, this indicator only depends on the probability, and it doesn't, so it doesn't matter whether we are looking at shapes, we're looking at animals, we're looking at values of something. It just depends on the probability, and it does so continuously. So that a small variation on the probability gives you a small variation on the indicator, and that makes sense. If you change the distribution a little bit, you want the variability to change a little bit as well.
Right.
Then, there is an assumption essentially that works for, let's say, uniform distribution. So the idea is that if you have a uniform distribution that is just, therefore the probability is just the inverse of the count, you want this variability to increase the more there are different cases. And again, you can't have something that measures variability that doesn't do that. If you increase the number of cases with a uniform distribution, the variability has to go up. There isn't.
Right.
The only thing that is a little bit sort of arbitrary, more of a convenience, is the third requirement, which is the linearity in probability. And this is a little bit complicated to write down, but essentially the idea is that you have a distribution, and then you expand one of the term in terms of another distribution. So you have a distribution of shapes, and one shape is the triangle, and then you expand the triangle in isosceles and all the different types of triangle. And so you are expanding one element through a distribution. Then you want to say that the variability of this overall expanded distribution is the variability of the original distribution plus the variability of the one that you're using for the expanded multiplied by the probability that you are expanding. And so this is a linearity in terms of probability, but again, it makes sense in a sort of heuristic way that the probability, we kind of want to sum the probability, but they have to be averaged with the elements that you're expanding on.
Right. In that basically there has to be some balance between, I mean, maybe triangles just have a few types, but if you're thinking about, say, species or something, then if there are a lot of reptilian species, but there's also a lot of just species, different kinds of species in general, then we want to sort of like weigh the relative variability within the reptilians, like within the reptiles, but also, you know, amongst the rest of the kinds of species of animals that there are. So yeah, that is, yeah, from that perspective, it is fairly intuitive. So and basically, which says that Shannon basically showed that the only quantity that satisfies all these conditions is the famous formula,
Right.
which is on his tombstone.
Yes. Yeah, so
Right.
of course, up to a constant. I mean, you could put a constant and you do the same thing, but that's just a matter of a unit choice. So
Right.
it matters from the physics perspective.
Right. And I mean, some version of that will come back when we look at continuous distributions and so forth. But at least for now, when everything's discrete, this is just an unambiguous way of characterizing the variability within a distribution. So from this vantage point, I mean, now that we know what it is, perhaps you could comment a little bit about the sort of segues into the other ways in which entropy is described. I mean, I understand that some of them are just plainly unhelpful, but I mean, why then?
Right. There is a connection, like the idea of disorder, for example. Well, in a way, it's a disorder. You can imagine that it's variability. So if you have more things spread around, you can think of that as a more disordered distribution. The way that it doesn't work is that if you have something that is extremely disordered, so if you take two gases and they are completely meshed into each other, then the entropy is maximal, but it's difficult to argue that the system is still disordered because now it's nice and uniform.
Right.
Sort of disorder works well when you have sort of at the beginning of the distribution of entropy, when you're mixing things a little bit, but then when it's completely mixed, it's hard to say that it's disordered. Let's say uncertainty also works a little bit like that. Like the more variability you have, the more uncertainty you have. The issue with uncertainty is that especially in continuous variables and so on, it's still associated to some, how can I say, some numerical value. So if I have, I'm doing, as you were saying before, a variability over animal, there is uncertainty on the animal, right?
Sure, yeah.
It doesn't work. But if you are doing things maybe in statistical mechanics and for example, you're relating like a measurement, like the value that you want to measure to the actual quantity that you measure, so you're basically getting the information transfer between those two things, and then it's sort of it's okay. Like it is a measure of uncertainty, and this is what I was saying before: is that each subfield has their own way that it sort of works for that, but then it does not work in general.
Right. Yeah. And I suppose we should go through the possibilities here, and I suppose you do somewhere in the paper. But basically the idea is that you know in certain cases we are just given a population of some kind of objects, and we're trying to characterize variability within that population. In some cases, instead, we're talking about probability distribution. So we have an ensemble over some possibilities, and we're trying to sort of characterize the variability within what can happen. And then there's yet another case where, and this goes to some of like this Bayesian stuff that you're describing, where we're not describing either of those. We're sort of describing some betting odds or belief. So this is sort of credence. And there's variability in terms of the distribution over your
over the belief. Yeah, so this is essentially ties in the fact that these P's can have different meaning. That these ways that the Shannon entropy uses, and it uses in a way that it doesn't really matter. Like when you were saying before, I have these cases and I'm making my histogram with the different cases. Well, what are those cases about? And again, it could different physical thing that exists at the same time. It could be one physical thing that exists, but I don't know which one. or it could be something that I think that exists, but I don't know which one I think in terms of my credence. And so, the wonderful thing is that in all these three cases, you're still going to have a variability. It's just going to be a variability on actual cases, on what could be, so a variability on what it is, a probability on what could be, or a variability on what I think is going.
It could be. Right. No, that was also very clarifying to know. But now let's come to this other aspect of it, which is that I mean, this is similar to what you described, but basically how you can use entropy, or what Shannon's goal was in defining entropy in sort of being a measure of quote unquote information.
Right.
So we've gone over uncertainty and disorder, and it's an odd thing perhaps to say, well, it's also a measure of some kind of information. So if you could please.
Right. So this is what I was saying before, is that the problem is the term information, because in some information there is this subjective feeling to it, like something gives me the information. It's basically based on how I weight the actual content of the sentence. And the point is that the variabilities do not care about the content. It only cares about which cases do you have. And so here we have, as an example, still two cases. One in which you have 50% chances of winning $1 million, and then where you have 50% chance of winning nothing. Or a completely separate case in which there is a 50% chance that you won $1 million, or a 50% chance that you won $500,000.
Right.
And this is from the variability perspective. These are two cases with equal chance, so they look exactly the same. But in terms of information, in the second case, I know that at least I have $500,000 to spend, which is good.
Right. No, indeed, and that also perhaps that sort of guides us for when to use other statistical notions, such as an expected value or a variance, where we're actually concerned with the value of some observable, as opposed to just entropy, which is just sensitive to sort of this variability.
Correct. For example, one of the problems, even if you have a discrete distribution with a bunch of values, you apply a transformation, a bijective transformation of the value. You scramble it around, add the 1,000 to all of them. The variance is going to change, right? But the variance has not, because the bins is still the same, the probability is still the same. And so the variance is a very different measure of the distribution than the entropy is.
Yes, no, indeed it is. So one other sort of bit of education in information theory that at least I lacked until I looked into a textbook, and perhaps several of my colleagues do as well, is the just to get a sense for what, why is this a measure of information, to sort of go through this question answer game of figuring out the number of questions. So I mean, this seems to be a classic sort of exercise. Sorry, I just jumped out, but I was just going to look for the specific place. This seems to be a classic exercise that's posed in various textbooks and other references when we learn information theory. However, not so much in physics. So could you please walk us through, for instance, this distribution, again involving animals, which we seem to be.
Yeah, animals are fun. I try to put animals because it was more interesting. I'm just writing a new edition of my book, and I have an example to show sort of to define dependencies. I have a rabbit farm, so one picture is and makes you automatically happier. So so the idea is as you said before, that this is something that if you come from the information theory side, as I did, this was a very intuitive way to start understanding the concepts, and it has to do essentially for a way to characterize the Shannon entropy, a different way, which turns out to be equivalent, is this idea. I have, again, I have my set, right, with a bunch of different things. I take one at random, and now you have to guess which one I've taken.
Yes.
So we can measure how difficult it is to answer that question, to identify the element by basically saying, well, what is the minimum number on average that you have to ask?
Yes.
And of course, you can imagine that if the variability of the set is bigger, you need to increase the average number of questions. And it turns out that the Shannon entropy measures as a number exactly that, the minimum average number of questions that one has to take or ask to get the answer correctly. And if you're thinking about in terms of, again, channel communication and transfer, right, those questions are then encoded into the bits that gets transferred, and that's information that Shannon was trying to look for. Like
right.
And so this idea of bit, one can be understood as number of yes-no question, because a bit of information is 1 for yes and 0 for no. So suppose that we have this distribution, right, with dogs, cats, and fish, and this is a fake distribution sort of made up to make the numbers work well more than anything else. But the idea is that you have this distribution of population of pets, and so you get a random person, and you want to guess what pets he has. Well, we see that most people seem to like cat, which is good, and you basically see that cats are sort of almost 50%, right?
Yes.
And so we want to maximize these answers. We want to group since we have a yes or no question, we want to be able to group all these answers in a way that we balance the tree, so that the first question we group 50% of the cases in one side and 50% of the case on the other. And so we would ask, is it a cat? And if it's a cat, we have 48% to get it. We're good at the first answer. Otherwise, we have to choose. And then we see that dogs have almost 25%. And so all the rest is going to have almost 25%. And so the natural question there would be, is it a dog? And again, if we do it, then we're great. Otherwise, we have to go and drill down the remaining 4 cases. Now, the remaining 4 cases, there is nothing that is really 12%. But you can see that 10 plus 3 is 13, and 4 plus 8 is 12. So again, we have something balanced. And so we would ask, is it a fish or a reptile? And then if it's yes, then we drill down between fish and reptiles. Otherwise, we drill down on the other. And so this is actually a standard way in constructing what is essentially an encoding scheme. We're basically assigning a string of bits to those different cases. We have assigned to cats, we've assigned the string 1. To dog, because it was just one question and it had to be true. For dogs, we assign no and then yes, and then it was 1, and so on. So you're basically assigning string of bits to all these cases. And so again, if you have a source that it's sending you the information, they can encode that information with those bits, and then you take those bits and now you can decode it and know, it's one of these.
Going back to sort of Shannon's original motivation, it's kind of clear as from this explanation as to why it was thought of as some kind of a measure of information or sort of the information content, because the encoding and decoding processes were implicit in, like, it was implicitly assumed that we had these, and so that whatever this bit string that came would turn into some information, like, okay, how many dogs or cats or whatever are there, as opposed to if we're just thinking about the entropy in the wild, and if without access to the encoding and decoding process, it would not mean all that much per se. We just having.
It's exactly what I'm saying. So the information is not in the bits. The information is in the encoding and decoding procedure. That's when you know what those things are representing. And this is true, even if I give you a file, right? And I don't tell you it's a JPEG, you don't know how to read it. So it's not information, it's just a bunch of ones and zero, but until you know what it is, you have no information. It's a little bit like, getting an ancient languages. It's just a number of scribbles.
Right.
Somebody wrote something down, but you don't know how to decode it until you know it's just gibberish.
Right. But even in that case, we will be able to tell how much variability there is within.
Yes,
within the
exactly.
So,
yes.
Yes. So I think, yeah, again, another thing that very much clarified the situation for me. So let's also move on to, so one thing that we haven't touched is basically what the combinatorial origin or combinatorial sort of path towards the formula for the Shannon entropy. And this is one that I've seen both in the sort of information theory and sort of general mathematical context, but also in certain physics treatments, especially when we think about, say, the microcanonical distribution, where we say we have sort of finely spaced energy levels and we're binning them, and we want to understand how to assign a sort of have a sort of density of states, and then we want to sort of take a logarithm of that density of states, and then you get this formula. So yeah, maybe we can run through that version as well here.
Right. So the idea here is that instead of getting, it's similar to the question, except that we are taking not just one element from the distribution, but we are taking infinitely many. And then we are looking at how many possible ways that we could have taken that infinite string. Right. And if you take a finite string, then of course you don't just get the combinatorics. This does not get you the Shannon formula. But if you take the limit, then and you take the Stirling approximation, then you find that in the limit that's essentially the Shannon formula. One of the way that I think it makes sense on a statistical mechanics sense is that if you have something that is actually a distribution of states, and you can imagine that it's a distribution of state that you have at a finite delta t, because again, nothing happens at points in time in physics. Like when we measure something, there is always a measure, for example, the temperature or something. Well, we need a delta T to actually measure that the temperature, the pressure, and so on. And so within that delta T, the system is going to be jumping around, and if it's in some sort of equilibrium for that limited delta T. If it's not at equilibrium, you're not going to even be able to define your temperature or pressure. But so if you have some sort of stability on that distribution, then in that ways that the things can jiggle, you're going to have a distribution that is going to tell you the relative frequencies of all the possible microstate or values that the system can have. And if you imagine a continuous distribution, a continuous function is actually mathematically identified by the value of an accountably dense subset. So if I know a continuous value, a continuous function on the rational, then since it's continuous, I can tell you where it is everywhere.
Yes.
So imagine that I start with the first two points, and I will have the initial and the final state, and I take a middle state, and I take the middle states again, and I take the middle states again. And so I'm creating a sequence of countably many states, like we were doing for creating the combinatorics. And once I know the full sequence, I will know exactly what is the oscillation of the trajectory that I had there. Now, because the system you're doing a macroscopic measurement, of course, you don't care about the permutations, right? So all permutations are going to be valid. You're not going to be sensitive to those permutations. So like all the permutations, and that it gives you a sense of how much was the variability when you were taking a measurement or variability of the system within that finite delta t. And that, of course, then it will correspond to something that is physically interesting, because it tells you essentially in how many ways the system can fluctuate.
Yes.
Right.
Wonderful.
So it's a physical thing that you get from this. And again, it's related still to this formula that comes out, because at the end of the day, it's like you're asking, what is the variability of these oscillations, and how many bits do I need to describe each element? It's always the same thing.
Right. No, and it is good to sort of clarify how the combinatorial definition really works in this asymptotic limit strictly. Like, I mean, to be on the nose. So,
yeah.
since you've already...
The thing that I like the most about doing these things is seeing the connection between all these different pictures, because what happens is, have a problem, you can then choose, okay, it's easier to see it from this angle. And so you can sort of play around with different intuition until you find the most satisfactory answer. And this is why I like doing the thing that I do, I guess.
No, it is a lot of fun. I mean, I'm glad there's people like you out there who are doing it with such focus. So we've already touched on this now, like we've alluded to it, but yet again, another source of a lot of confusion, at least for me, had been understanding how to make sense of entropy with the case where you have a continuous distribution. And in particular, in a lot of the I don't know how to put it, but like in a lot of sort of physics related, so contemporary physics related exercises, this is sort of implicitly what's going on if we're talking about, say, it's entanglement entropies in sort of field theory settings, sort of quantum field theory setting, then you have to assume that at some level there's a continuous distribution, which, okay, maybe in some secret way came from some discrete one, or in other ways where speaking of contemporary trends, if you think about what happens in machine learning, that if you think about data distributions, of course, in practice, they're discrete. But the idea, I mean, a lot of the statistical modeling goes into trying to treat them as if they were continuous and sort of like seeing how far one gets, and a lot of the generative modeling that now has captured everyone's attention is again based on sort of minimization of a certain kind of entropy. Well, it's a relative entropy, but yeah, so here, what I really liked was both your presentation of the idea, but also clarifying what it means to have a negative entropy. So, yeah, please walk us through the.
So the first thing I'd like to say, so one of the things that in physics we don't seem to have understood well is the difference between discrete and continuous.
Yes.
In physics, we still have this idea that, the continuous is like the discrete, just with many points, with more points. And it's not like that. Like that there are some things that qualitatively are different on the continuum than on the discrete. And then mechanics is even more different because it mixes some features of the continuous and the discrete. Yes. And it's not something that I'm actually probably I didn't have clear ideas back then when I wrote this paper. Now I have clear ideas. So that's sort of a source of a lot of confusion. So one of the issues when you go from the discrete to the continuous is that the nature of the probability changes. So on the discrete, we have probability. We say this case has probability, I don't know, 1/3. So we have a finite number associated to a point. When we are on the continuous, we don't have a probability for a point. We attach a probability density. And the probability density is even dimensionally, right? If we're taking a distribution over position, it's going to be unit of probability over unit of distance. But it matters which unit you pick. Because if I take the rho of, essentially probability over kilometers or probability of a meter, there is a factor of 1,000 between the two things. And that will show up in the entropy. So what really happens is that whenever you do probability on the continuum, when you do density on the continuum, the unit that you chose is embedded in the quantity that you're using. And somehow we don't think, I don't know why in physics, like we do unit and dimensional checking, I don't know, up until you do classical mechanics, thermodynamics and so on. And then at some point you stop and you said, oh, these units, I don't care about it anymore. I'm doing quantum field theory. And completely you get confused because you don't know what you're talking about, because we can only talk about things that we measure. And if we measure them on a continuum, we have units, and the units matter. And so here in the entropy is a little bit interesting, because we said that we wanted something that only depended on the PIs, on the probability. It didn't depend on what were the things that we were distributed on.
Yes.
The thing is that we are actually depending on the row, but the row depends on the unit. So it's no longer true on the continuous in general that our entropy is going to be independent on how we label things. And so here it is important. And what happens is that you're essentially comparing the entropy to the entropy of a unit uniform distribution. So you take a distribution that is on one unit, you call that a zero. Now, that it's more spread, that has higher variability, is going to have a higher entropy than zero. And instead that it's more tight, because we can get infinitely tight. Like in the limit, we're going to get a delta Dirac. A delta Dirac has zero support. It has an infinite value. That's going to have literally entropy of minus infinity. But it's a relative entropy between, between the unit that I chose and whatever other entropy it was. So it's called, in fact, entropy. And the negative entropy just means I have a variability that is lower than the unit. But then, of course, I go from a unit of 1 meter to a unit of kilometer. I've changed the zero. And the things that were negative maybe become positive, or vice versa.
Oh, no, that's great, because indeed, well, one of the points you're making here is that in the continuous case, we are forced into thinking about all entropies as essentially relative entropies, or sort of all probability distributions as being sort of relative to this distribution of the bins in some sense, right? So I guess you describe it here how it works with just a distribution over half a unit, and what it means, because you basically have to sort of lose one bit of information to widen the variability back to one. And what you mentioned with the Dirac delta is like the extreme case where we're going back all the way down to zero support. So basically, this also relates to the other issue, which is when we change units, we better be careful that the quantities we're dealing with are actually sort of invariant under these changes. And well, the fact that you can change units and get from a negative to positive entropy means, well, it's actually not strictly invariant, right? It's important in an important sense. It isn't. So yeah.
But it's even worse than that when you make a nonlinear transformation, because if I just make a linear transformation, everything gets stretched or shrinked in the same way. So if I had two distributions that had a difference in entropy, I'm just moving them up and down the same, so the difference remains the same. If I'm making a nonlinear transformation, maybe I'm stretching here and stretching here and shrinking here. Then, if something was distributed mostly here, it gets mostly stretched. If something is distributed here, it gets mostly shrank. And so maybe two distributions that have the same entropy might end up with having different entropy, or two things that have different entropy end up having the same entropy. And again, you can imagine that this is particularly bad if we want to have thermodynamic entropy be a coordinate invariant quantity, such that me and you can agree that the entropy is remaining the same for a process, and that we have a deterministic and reversible process. Because if we can't agree on an objective value of entropy, how can you even talk about thermodynamic reversibility or reversibility? It would be, I have my view, you have your view, and nothing would work.
Of course, right. And mathematically, it manifests itself through the logarithm of the Jacobian, which also gives us
it's the expectation of the logarithm of the Jacobian, and see that there is a dependency there on the distribution, such that each distribution will pick up the Jacobian in different parts.
Right. And that actually brings us to a point that you make here, which I had not appreciated um, before in any way. And I'm actually curious to hear if there is a story for how you came to this realization that it therefore matters on what space we're looking at these distributions
Yes.
on. And
Yeah.
that there's very important use for the phase space when we're doing this because of how these Jacobians are treated. So yeah. When did I mean? Okay, first I guess we can walk through what the resolution is, or sort of what exactly I mean by this, and then I'd be very curious to hear at what point this became obvious to you.
Right. Okay, so we have this issue, right? That if we want to define, for example, like one good way to look at it is this, right? Is a uniform distribution over a finite or a compact set, right? Of a set of finite measure. The entropy that maximizes the distribution that maximizes the entropy there is the uniform distribution. So if we want to have the same notion of entropy, me and you, we need to agree on what distributions are uniforms and which are not.
Yes.
And from what we saw before, if I make a general coordinate transformation or unit transformation, I will have something that looks to me uniform and not to you, because I take x and you take x to the third. And so you see something different. This is actually a problem in interpretation of probabilities called the idea of being able to assign a uniform distribution is called the principle of indifference. And it's a known problem in the foundation of probability that you can't apply that on the continuum. Again, because for example, if I make an assumption that I'm indifferent on the size of a cube, for example, right? So that I know that the cube, the side of the cube is between 1 and 3, and then I say, well, any of the intermediate thing could be fine. I could take a uniform distribution between 1 and 3. But you could argue that by the same reason, the volume goes from 1 meter cube to 9 meter cubes. So you would be able to say, okay, I want to have a uniform distribution on the volume. And of course, if I take a uniform distribution on the side and you take it on the volume, these are not going to correspond. The expectation value is not correspond, right? So there is an intrinsic problem of defining this uniform distribution on a continuum.
Yes.
And what I don't know how we fail to realize this, but physics has exactly the structure that we need to talk about uniform distribution in a way that it's invariant. How does it do it? Is that when we do statistical mechanics, it's very important that we use position and conjugate momentum. If you try to do statistical mechanics on position and velocity, you get the wrong answers. Why do you get the wrong answers? Because what happens is that position has a certain unit, and when you change position, momentum change in a way that is covariant. Therefore, if I increase my unit of, if I stretch my position, my momentum is going to shrink. And if I shrink position, my momentum is going to expand. And what's going to happen is that the area between the two, the dq times dp, will remain invariant. So space. This is funny because if you do statistical mechanics, you talk about the Liouville's measure and how it's conserved in time, right? And how it's important. But even more important is that it's conserved under coordinate transformation.
Yes.
If it would be conserved in time, but weren't conserved in under coordinate transformation, me and you couldn't agree on what the entropy was.
Right.
The thing. So we have a fix in physics, very interesting enough, and we sort of never see it, that it's already there in phase space. And curious enough, phase space is not only fixes this problem, but it's the only space that fixes this problem. If you say, I want to create a uniform distribution in a way that are coordinate invariance, the only way to do it is this. You have one unit, and you have a unit, another quantity that has the opposite behavior with under unit change.
Wow, I see.
In fact, another paper on the philosophy side that it basically says, I think the title is something like classical Hamiltonian inequality is equivalent to conservation of entropy, where we basically argue that point, is that you get the structure of phase space from the invariance under coordinate transformation, and then you get invariance over time by asking that the areas, the information entropy is invariant. So this is something that I find fascinating because we are taught, we're used to think that the statistical mechanic is somehow a layer that you put on top of mechanics. But it's already built in the mechanics. And so it's incorrect to think that statistical mechanics is something built on top of classical mechanics. It's the two comes together because you actually have the exact structure to be able to do both.
Oh no, that is very fascinating. So when was it that this realization came to you? Like, if you recall, or maybe it was one of those.
It was probably in 2012. So when I transitioned to do these things more thoroughly was so again, at some point, I was like probably everybody else. I was trying to figure out the quantum mechanics and stuff like that, right? At some point, I had a realization and said, okay, but what does it mean to understand a theory, right? And my answer to that was, well, I feel I will understand the theory if I have some starting point that don't even need to be necessary. It could be just assumption that I take in this case. But then I know that the whole theory can be derived from there such that I understand it because I only have to understand those initial assumptions. And so that was my goalpost for saying, okay, I want to understand quantum mechanics in that way. I realized that, oh, I don't understand classical mechanics that way.
I see.
Because why do we have conjugate quantities? What is energy? The vibrational principle, the principle of station. Yes. Why do we have that? Have a Lagrangian. What is the Lagrangian? Why is it the Lagrangian can be changed and the system does not change? I didn't have, now I have, but I didn't have questions before. And so it sort of said, okay, well, maybe we should set aside the quantum mechanics and go to the theory that I think I understand and I actually don't. And then I tried again, trying to find, so right now we call this process reverse physics. You start from the theory, you try to figure out what are these things that the theory does, and then try to find the physical justification for those, and then you want to find the minimal set of physical justification that give you the theory. And one of the things that I noticed was this invariance of the area. And then I said, okay, well, can I make sense of that? Is it something that I need, or is it something that it's definite? And then I realized that not only like we need it, but it's like without it, we can't do anything. So it's really a starting point to be able to do anything else. And there are things like that hidden in our physical theories that we realize. It's just that we never look.
Right.
Physics, we're always wondering about the new shiny thing, right? Oh, the quantum gravity and so on, right? And so I've taken this completely different route and say, okay, let's go and look at the details of these other things, and there is actually a lot more than I originally thought there would be. So.
No, that is humbling, and I mean I agree. It's oftentimes what's difficult about even some of the sort of contemporary questions is not actually inherent to them. It's really just more of a lack of a thorough understanding of fundamental concepts. And there are a lot of debates that I notice which are essentially there's nothing to them. It's just that there isn't an agreement about what the question is. And yeah, no, but perhaps one day we'll with the fine work of people like you, though you're very few in number.
But there's no
Be
funding
able
for doing these things, which is another
Of
problem.
course not. No, of course not.
It's
And this
difficult
is
to get your paper reviewed because people have, their niche, but then if you go around a little bit, journals. I have a paper right now on the geometrical and physical significance of the action principle, where we go through the details of exactly. It has been rejected without review by 5 journals. We're struggling to find somebody.
Yeah, these are. I mean, I can completely see that this is the kind of roadblock you would run into. And I have friends who, having noticed similar trends, just decided that they should become or write sort of philosophy journals. And I don't know if that's something you've considered or.
Right into philosophy. So we already have. We have another one that is under review, and hopefully, but it's not a pleasant experience.
Of course.
One of the problems with philosophy is that it is never enough to just state what are the things that you are saying. You always have to be inside some sort of discussion and so on, right? And so,
interesting. Okay.
If the thing well, it's a little bit like that in physics. It's just the difference is that you can mainly do something in the introduction that says, okay, I'm relating this to these things, and then go in the bulk. But a lot of the time in philosophy, you're expected to argue against someone.
Okay.
Right, and that also means that you have to have, let's say, a much deeper knowledge of the history of the discussion, and so on. And so, coming from the outside, it is really difficult. So
I see.
There are, like in any other field, the sub-disciplines. So if you want to talk about classical mechanics, well, there's these people, and in quantum mechanics there are these people. And so if you're something interdisciplinary, there is still that issue. I mean, I was invited to write a paper on a philosophy journal for an issue on a special issue on time. And at some point, I realized, I'm not gonna have time to go and do all the research. Like I have a lot of things to say, but I don't know how to. You need to use the right words such that you have to talk to discuss things in a particular field that has their idiosyncrasies, their vocabulary, and each sub-discipline has their own. It's so what we're trying to do is to find collaborators in the different fields,
right,
and then try to develop something with them. And
I see.
Does not work very well because in philosophy people privilege single author papers.
Oh, I see.
So collaboration is not seen. I mean, we had a graduate student here, and we did one, but the idea is that I can do this one, but I need to write my own literature so that I can get tenure somewhere.
I see. Well, I mean, the one other option, at least for the purpose of paper clarifying the role of action principles, and I don't recommend you do this in earnest, but this is just something that came to mind, would be to try to go after the optimization literature, where there's a lot of I mean, there's a lot of room to play. I mean, it wouldn't be hard for you to find perhaps some problem where you can kind of cook up an algorithm where you say, you see, we do better in this. I see that it's maybe not the most appealing thing, but
I mean, it's for this particular paper. I'm sure at some point we will find somebody who will actually submit it to reviewers, which would be like a step forward. No, but I think it's more how can I say, a description of the status of the field, where
no, I agree, it's an indictment of it, indeed.
You would think, like, we all study the action principle, and it's always described like this magical thing that comes out of nowhere. So somebody the paper that claims actually there is like physical justification. I tell you why the Lagrangian is defined. I tell you exactly geometrically what these things are. So it's something very precise. So you think, well, this is applicability at least in every classroom because everybody's learning this thing.
Yes.
But somehow it's not. And again, it's not the physics community that is not valuing it, right? It's the editors that are in charge of the journal. So the incentive journal seems to be in a way that they're not interested in that thing.
I see. Yeah, and then, well, very unfortunately, the currency of journal articles is still one that affects all of us. So
Yeah.
there's much to be done about that, and hopefully, well, with discussions like this, I mean, mine I have a very modest following, I must say, more modest than your channel even, but
I started
the
early.
hope is that the hope is that it'll eventually reach the eyes and ears of the younger people who are actually entering the field, and indeed I do notice that at a certain point people are grateful for the things they learned well when they did learn them. Yes.
Oh, I get a lot of emails from like videos and from some people like you that found the article thanking me because it clarified for them, and so again it means that there is. I can also tell you this paper was first submitted to another journal.
Oh.
With 3 reviewers. One of them said, I usually have I'm usually very critical with papers, but I have to say I have nothing to say. This is perfect. This is greatly going to increase the understanding of this. The second one was, oh yeah, I guess it's nice. It's reviewing up a few things. Okay. And the third one was, it's all completely wrong. And this is like 3 pages of.
No, that's so interesting. But they overruled the other 2.
No. It was rejected. I had to go to another journal.
Oh wow, I see.
There is a lot of random. But again, I would expect, if somebody comes in with a different way of looking at things, that's exactly the type of reaction that I would expect. Like the one that understands, oh, this is a new thing, oh, this is really important. The other one that sort of doesn't see the thing, but said, oh, okay, whatever, that sort of flies past their head. And the other one who has the strong negative reaction because he's used as seeing the things in the way that he wants, and now comes in a different way. Right? So it's justified for me that the fact that there were these 3 types of review, right?
Yeah.
To the editor to say, okay, well, which case it is, but
yes.
But what happens is it's easier for the editor to say, okay, well, go to another journal. So we did. So
yeah, well, I mean, it's a missed opportunity for them because I mean, they really do. No, I must say, I mean, the thing is that they do tend to care about these. They have some notion of respectability and this and that, which is only somewhat paper thin. In that I've seen a lot of papers that get published, which, okay, there isn't anything wrong in what it is they do. There isn't anything. Perhaps the researchers that wrote them were also good and were capable of doing better. It's just that out of the necessity of how things work in our profession, this paper had to be written. It had to be submitted to a journal. It had to be published. Very likely, no one will actually read it. Or those such as I who end up reading it, we go, well, why do any of this? And then this isn't a sort of deprecation in quality that seems to be of concern, whereas on the other hand, we have some people talking about sort of more fundamental things, and just because they are sort of from 50 miles, look sort of similar to some of the crazy emails we get, all of us, that they don't want. So, well, I mean, such is life. But yeah, I suppose to conclude, we can sort of
let's continue
together with our with everything we've learned, and perhaps this is the easiest section to go through, which is the applications within statistical mechanics. So I guess we've already touched upon why we should be thinking about densities in in phase space of these many body systems. But yeah, please walk us through like the different notions of entropy that still exist within within this context.
Right. So the main two that we have are the Boltzmann entropy and the Gibbs entropy. With the Gibbs entropy, the Shannon entropy applied on phase space with the correct variable. Because again, if you do if you do the Shannon entropy on position and velocity, you just get the wrong thing. Right. And there is a connection actually between the two. So I don't think I have it here, but
okay.
To think about it, suppose that so the sort of the log W, you're basically putting a uniform distribution over a set with finite measures. So the Liouville's measure basically counts the states that you have, and again. Yes. It's a volume, so it's volumes have a finite measure. Points don't have finite measure, and if you take one of these volumes and put a uniform distribution over it, then the Shannon entropy actually becomes the Gibbs entropy. So they're not completely unrelated. And you can also go the other way around. So here we sort of derived the Boltzmann entropy from the Gibbs entropy, but you can also do this trick. So suppose that you have the phase space of system plus environment. And you put a constraint. So you are, I don't know, in some kind of ensemble, and you have the energy, the sum of the energy is fixed, right? But you are fluctuating with a constant temperature from one to the other, right? So you essentially on the whole system, system plus environment, you put a uniform distribution. But then what's going to happen is that you're going to take the margin of that distribution over the system itself, right? And so that's not going to be uniform anymore because it's going to do its different things because of the constraint. What happens is that in the limit that you have equilibria and so on, you are going to have a Boltzmann distribution on the system, and the entropy is going to become the Gibbs entropy on that Boltzmann distribution. So. Right. Like you can basically recover the Shannon the Gibbs entropy in that case by basically putting essentially a uniform distribution over the combined environment plus system case. So they're not completely unrelated.
Right. No, that's very fascinating. And of course, prior to coupling the system to a bath, there's the precursor, the sort of microcanonical entropy, which again connects back to the combinatorial type of definition we had before, where we imagine we have some collection of finely spaced energies, we bin them, and we just use the same argument as essentially as Shannon did, except now we're just thinking of bins of energy. Yeah, and I feel like here it's sort of fairly clear, having discussed everything we have, how it all sort of comes together, and that was very satisfying. The one thing that I don't know, like people must have heard of, but it's not standard notation always, is this notion of the gamma space. So
right, so that's more of a historical thing. So there was a period, right? I would say before Jaynes, where it was not clear whether the Gibbs entropy or the Boltzmann entropy were the correct one, and the idea was that you could create. So there are two types of things that you can do in terms of distribution. You could take the phase space of a single particle,
yes,
then put an actual physical distribution that tells you how many particles you have in each state, right?
Yes.
So distribution is not a probability distribution, right? It's not what could be, but it's what there is. There are 3 particles in that state, there are 5 particles in that state, and so on, right? And then you can compute the variability of that distribution, and it's going to be the entropy of that distribution. And sometimes this is called the Boltzmann entropy. The Boltzmann entropy is the one uniform. There is complete confusion when you read so if there is one takeaway for the people that are viewing, whenever you read a paper on statistical mechanics, go back and look exactly what they call the symbols, because some people call the Boltzmann entropy one thing, some people call the Boltzmann entropy another thing. And again, I've seen people talk past each other because they're using the same term for different things. So there is this type of distribution where you count the number of particles for each state. And then you can do instead what you typically do in the Gibbs entropy. You take the product of n single particle state, and then therefore the point in that space is the full configuration of all the particles.
Yes.
And then you put a probability distribution of that. So each point essentially represents a distribution of the other case, because it tells you how many particles are there in all states. And then you're doing a probability distribution, or therefore of what could what could be. You have one thing and what could be. And so there was this confusion that you had one type of entropy, again done with the rho log rho, on this space of a single particle, and is that the gamma space? I always forget which one is which.
Yeah,
the one.
So let's see. So the distribution over the 6n dimensional phase space of n particles. So where this is like the kinetic.
Okay, so the gamma space is the 6n. I was like names I have always to really look at them. Okay. So there were these two types of entropies. That sometimes the Boltzmann entropy is essentially the variability of the distribution of particles, and instead the Gibbs entropy is the variability of the probability distribution.
Yes.
And James was the one that, at least my understanding, which I'm very bad at history of physics, but one of the one that said, no, this is the one that is correct, because what is that if all the particles are identically distributed, then everything becomes the full probability distribution becomes a product, and therefore you might as well use the number of particles in each state. It doesn't matter. But if the particles are not identically distributed and you have correlations between them, then this doesn't work. It just gives you the wrong computation of entropy. And so,
right.
Again, in some textbook, you find the old Boltzmann understanding of entropy that is based on that single particle distribution of single particle phase space, which is not the physically correct one. Again, and this is the misleading thing, is that in the example that it's used, it's working because you're considering, for example, things that are picked at random by the same distribution, therefore they don't have correlation, then they're identically distributed, and therefore you get the right computation. But then you think that same thing generalizes to the general case, and it does not.
Yes. No, and this is actually another sort of blind spot is sort of what happens away from equilibrium in general, and and no, it's important to know which notion of entropy to use. So if I may jump briefly, so this is basically the entire paper that we've more or less covered everything here, haven't we? Well, I mean, there's this one more bit about the von Neumann entropy in quantum systems. Which I mean, again, like if you want, we can cover before I
the difference of the von Neumann entropy is more a difference of the space, more
the state space.
So what really happens that is different in quantum system than in classical system is that in classical system you have a single decomposition. So if you have a mixed state, you only have one decomposition in terms of the pure states. In quantum mechanics, it does not work like that. If you have a spin 1/2 system and you take the maximally mixed state, so the center of your block sphere, Well, you can have it by an equal mixture or up and down, or an equal mixture or left and right.
Yes.
So essentially, the difference between classical statistical mechanics and quantum statistical mechanics, which then percolates also to the mechanics itself, because the mechanics itself is just a motion of the pure states.
Right.
And so the von Neumann there is essentially there to take that into account.
Right.
But a lot of things are the same. Then is what I was saying before, is that there are some particular, and it's not discussed in the paper, but the quantum state space has some feature that are like the discrete, the classical, and some other feature that are more like the
continuous.
And so it sort of strides between the two, creating even more confusion. So it's like the continuum, and in some other ways, for example, it's bounded from below. The entropy,
yes.
Discrete distribution in classical mechanics is bounded from below at 0, and instead the entropy on continuous distribution, and we saw the delta Dirac is minus infinity, has no lower bound, right? And so sort of quantum mechanics puts the lower bound, but you can still create this continuous distribution over the state space. Like if you imagine again your block sphere, you can put a continuous distribution such that you have a probability density in each direction of the block sphere. That's still allowed. So.
Right. No, well, no, that's great. Yeah, and again, just knowing that there's there's important roles being played by these physical state spaces is greatly beneficial. Then that kind of takes the confusion away from the entropy and sort of like, clarifies what's going on. So I thought maybe you would appreciate this this blog post. Yes. So if you just started by knowing that relative entropies are of this type, that that they're positive, you can deduce an awful lot from that. And so he starts by saying, okay, let's just take this basic fact and then go through a series of definitions. And here, of course, one has to be careful about which notions of entropies get used. But you just go through a series of definitions and you come up with statements such as the Crookes fluctuation theorem and the Jarzynski equality. And that these just come from just plugging in definitions and expanding the numerator denominator in expressions like this.
Okay.
And now the sort of interesting upshot of it is that it also features in a lot of contemporary machine learning. For instance, in these variational autoencoders, there's this so-called evidence lower bound or ELBO, which is yet another manifestation of this this fact. And there are these sort of more newfangled machine learning methods like called diffusion models. And there too, starting from this basic fact, you just break up the distribution in sort of more and more fine-grained ways. And you basically understand why these methods work as well as they do compared to all the rest and so on. So this is just to say that the scope of or the need for a better understanding of like entropy and so forth is very much percolating into very relevant sort of engineering questions. And I feel like there is just a lot of understudied aspects of it for the extrapolation. For instance, we talked about the importance of physical state spaces and how, in order to ground our notion of entropy when we're dealing with continuous distributions, having physical state space is very important. Now, in a lot of what I see, I mean, the implicit in a lot of these formulae are just the fact that there's continuous distributions, but these aren't physical state spaces. These are just, they're in some sense whatever the data modality wants them to be. So, well, what's going on there as an example? And second, well, I mean, what you basically explained was that every continuous probability distribution has an entropy that is itself a relative entropy between the density you're interested in and some density of bins, right? And there's a sort of this essential notion, which not only is relevant to maybe the kinds of questions that we just looked at having to do with machine learning, but also there's a lot of literature, or not a lot, but some very nice literature in the quantum field theory, sort of like entanglement entropy in quantum field theory, a story that makes this, sort of exploits this fact, that says that every entropy is actually secretly some kind of relative entropy. And perhaps, I mean, this is just, I guess, a recommendation, is that perhaps this sort of provides some avenues for where you can kind of sneak in sort of literature. Like, if you could find collaborators, you're like, well, all we really needed. I mean, it's of course, I mean, you should just write papers in earnest, but I mean,
so yeah, so the KL divergence is not something that I am so familiar with, because again, so the way that I understand the KL divergence is essentially a measure of, let's say, information transfer from one variable to the other.
Right.
And in that sense is relative, which is a little bit different than the sort of the relative Shannon entropy, which is just you're doing it on a continuum, and therefore you just have a unit. It's kind of related, but different. The thing that interested the most is again the entropy that is related to physical systems, which again is from the one that you use in information theory, because in information theory, and not just information theory, I mean, when you're taking measurements, right, at the end of the day, you are doing these a transduction of one variable into another variable into another variable and so on.
Exactly. Yes.
And there the KL divergence is important because you have all these chains, and maybe you take, you have two things and that you're measuring, and then you put them together, and there is all sort of things that I don't understand that can happen and that people study. The thing that I'm interested more is, at a physical level, right? Again, this idea that when we talk about states and we have a distribution over states, we still want, in a relativistic sense, of those things to be invariant. Yes. There are states, no matter what I do, no matter how much knowledge we have of those states and so on. And this is one of the drawback of people learning information theory from the machine learning type thing, because again, what we were saying before, machine learning correctly, they use probabilities as credences, because that's exactly what they're doing. But then taking that and bringing into physics and say, okay, well, sorry, like you can believe that the temperature outside is 20 degrees, but if it's 3 million degrees, it's 3 million degrees. It's your credence on the distribution of the Boltzmann entropy. It's a little bit.
But the subtlety there is that nowadays, especially with these generative models, let's just take the language models, the most famous ones. Mm-hmm. So what they actually do is much more akin to modeling how should I put it? Like, I mean, this isn't exactly what they do, but basically they're very sophisticated ways of modeling sort of actual statistics within language. So basically that, like, we just look at sequences of characters or sequences of like subword level things, and what they're trying to do is sort of learn the relative, like, what is a sort of relative frequency between different occurrences of
and it's
letters.
Amazing how much you can get away with it just by doing that. It's really
right. And so there, I mean, in some sense it's credence, but in another sense it very much is I mean, the reason they're so good is that they very much have come closer and closer to approximating the distribution
right
over.
So, and this is where you go with Bayesian statistics, the idea that you set some prior and then you keep updating your probability based on new information. The issue with that is that, from my understanding, by talking to people that know a lot more than me on foundations of probability, these tricks only works in the finite. So if you have a case that it's countable, or even worse, continuum, the prior, the final distribution is going to be very sensitive to the prior. So what happens? You would want this algorithm to, no matter what prior you said, no matter what your initial credence distribution, that you're able to find at the end the correct one.
Yes, yes.
And again, in this machine learning model, well, the memory is finite, the number of things is finite, right? And so you're safe, even though it's mind-boggling high, because it's I don't know how many petabytes or whatever they use, but it's still finite. So at some point, with enough data, you're going to converge, and you're going to converge to essentially the same thing. So that works in those. So when we have bigger state spaces, that's where the things become a little bit tricky.
Right. But I mean, let's sort of examine this. So, I mean, this is just another motivation to maybe find machine learning collaborators or some people that would make it possible for your papers to, reach the audience. But I mean,
I don't want to complain too much. I mean, we find ways to publish.
Okay. I mean,
it's just that it's the number of circles that you have to go through. It's.
I know, I understand it's frustrating, but it is actually a concern that I have heard articulated in that world, which is that language modeling is all well and good. It's great because ultimately vocabulary sizes, even if we're not just taking literally characters, but if we're taking like segments of words, it's finite, right? And we just have some distribution over that. That's fine. The issue comes when we have to imagine, well, what are we going to do with video, right? So like, video, of course, the frames, it's all technically finite.
It's so fine, yeah.
Nevertheless, if we did, like in the sort of essentially the mathematical modeling they're trying to do, understand it to be continuous, to essentially try to treat it like it's continuous, perhaps that would be the route to having sort of like workable algorithms. For instance, if we're describing like integrators for numerical problems of various kinds, even when they aren't actual sort of Hamiltonian systems, it very much helps to pretend or cook up a Hamiltonian, because having the symplectic property even at the discrete level, it's energy conserving. It has a lot of advantages. So I mean, in that sense, this is why I also said, maybe this action principle and all of that, it's targeting something like optimization or some engineering heavy discipline is maybe
so
a good
that
thing.
I didn't know. So they, even in the discrete case, they try to have a symplectic structure to do stuff.
It helps. So the idea is that if you have, I mean, it typically also goes with wanting an autonomous system. So there's also you cook up not just some, like you cook up a conserved Hamiltonian, right? So when you try to do that, then what happens is that normally you can assess the quality of a numerical integrator through something called the backward error. So you sort of like find, like you basically see what is the modified continuous differential equation, whose sort of Taylor expansion around the appropriate point is exactly what my integrator is doing. That this is like the game of backward error analysis. And you find that, okay, I mean, like the most of the naive ones, you sort of see that, okay, you have to do a whole bunch of fixes in order to get them to work. I mean, the error, so you can sort of bound it maybe polynomially. But now, if you do this with a symplectic integration scheme, then all of a sudden it goes all the way down to exponential. Right? So exponential suppression in the actual step size, provided your integrator is symplectic and consequently, like energy conserving. So how they check it is through energy conservation, but basically you're just taking, like, making sure that you're discretizing the Hamilton's equations properly, giving the momentum and the position the right relative time step, knowing that the momentum is like the conjugate variable. And it's so it works really well. You can sort of give more assurances that within I have some measure formula, say, by just looking at the Liouville measure on the continuous phase space. And if I know that my dynamics is mixing, then even when I discretize everything, the idea is that, well, actually, it's gonna land up in a very similar sort of part of the state space that you anticipated. And this sort of stuff is used to great effect. And sort of like, similarly is why I was thinking that, like, well, I mean, if you have something like a notion of entropy that's able to sort of or sort of you've identified what allows you to define these things well when you have continuous probability distributions, and especially if whatever process you're doing is just applying multiple nonlinear transformations to your to your data. And what's more, some of these nonlinear transformations it's important. So a notion of equivariance is important in these algorithms, especially in computer vision. This is something that people have noticed, that they need to define these networks to respect the sort of mundane sort of translation, rotation, etc., all these invariances that we as physicists would readily acknowledge. I mean, I can't help but think that, again, like if there was a way to not just think in terms of optimization, but also in terms of actual statistical modeling, that there ought to be some notion of a physical state space, that maybe you can actually, get a generative model for an almost continuous data modality to work out to work out well. But this is just
no, it's interesting. I didn't. I wasn't aware that people were doing that. So I
mean, I don't know that they are. I'm just saying that this would be a this would be an angle.
No, but you said that people do try to find a symplectic form of.
Yes. That's
that part I didn't know. And I can sort of understand like why it would be appealing, because again, if you have a symplectic form and you are, let's say, evolving a probability distribution, you have this guarantee that the values of the densities are mapped one-to-one. The value is exactly.
Yes.
And not only it sort of it unpacks for locally orthogonal degrees of freedom. And so, like, if you are clever, probably you can move the marginals well as well. And then I can see that having that guarantee somehow embedded in your algorithm, you get less this error going forward, because you have one less source of error, which is how much did my distribution go up and down. Now I just don't know where it was. Maybe I haven't. But I know that the value was that, so I can see why that would make sense. I just okay. So you have a discrete model, because I know that any system of equation can be turned in a Hamiltonian system just by adding the same number of variables, right? So you can always do that, and you can always put a symplectic form. And again, there is some convenience that the people might do that, because I don't know. It's like when you add it's probably the same exactly. When you do complex analysis, you have your integral on the real quantities. Let's add an imaginary thing. And then somehow on the plane is much easier, and then you take the other side out, right? So, but I didn't realize that people were doing that also in the discrete. That's
yeah. And I think that this is well, at least some of my colleagues here have for instance recently written some papers about optimization and so on in sort of machine learning venues, and they had an excuse to have an appendix introducing like Hamiltonian mechanics. So like this is just this is just an anecdote that inspired me to point in that direction. But it's just, I don't know, something to consider, because like another way to put it is if.
Yeah, there are more connections than than I realize it.
Yeah, but exactly. Yeah. So anyway, well, you've been very generous with your time, Gabriele. I appreciate it. And if please let the listeners know where they can find you and your other papers, your project, and everything.
Oh yeah, so my project is called Assumptions of Physics, and if you Google Assumptions of Physics, that's gonna be the first hit. I also have a channel on YouTube, and you probably find it just by looking for my first name and last name. And what I put there are basically results of the research. So trying to show you the geometry of phase space and other things like that. I have a video on the interpretation of physical and geometrical interpretation of the action principle, like the simple version that only uses vector calculus. Then there's a different paper that goes into symplectic geometry, which of course nobody knows. So it's difficult to teach something. But yeah, so I have those things, and one of the things that I'm trying to also do is essentially, in principle, I'd like to extend this project more and find more people to collaborate and contribute. So that's something that it's an ongoing question. And I also should put more videos. I have some routinely people, I should put more videos, and I should. It's how you find, like, if you find it easy or not and sometimes I feel that my bar is too high to put anything on YouTube.
Oh yeah, well, no, I know what you're saying, and I mean, I've just I take shelter in the fact that I essentially just have a handful of viewers, and most of them are just my friends, and so they'll forgive me. But I mean, for those who are listening, if you've come this far, please like, share, and subscribe. It really helps the channel. And, I'll catch you all again.